So last time we already reviewed in details the first 3 sections. Now I started also already to introduce the cross product. So actually I told you already last time that if I look at my syllable, which I get from my department, they tell me that what is presented in section 12.1, 12.2 and 12.3 should be known, but the rest is not reviewed. But I assume that what you find in 12.4 about the cross product and 12.5 about the plane and the line in the 3-dimensional vector space. Also this is already known, and you have learned this in high school. So you have learned the cross product already in high school, right? So I will maybe in chapter 12.4, the only thing which is new for you is the scalar triple product, something which you might not have seen in high school, but something which is rather trivial. So we will I will just spend very briefly to introduce once more the main properties of the cross product. Okay, so there are actually 2 different ways to define the cross product. Last time I used the following definition. So we have 2 vectors in the 3-dimensional vector space. So I just want to once more emphasize this notation which is used in our textbook. So V3 denotes the 3-dimensional vector space. So you can more or less think about it as R3, R to the 3, but of course it's different because the vector space has some structure, like you can do addition and you can do scalar multiplication. So it's slightly different from an algebraic point of view. Now, so we have 2 vectors, and we introduce coordinates. We introduce coordinates in a standard way, so we can denote, or we can write the components of this vector as A1, A2, A3, and of the vector B1, B as B1, B2, and B3. Okay, and then we define the so-called cross product. Okay, and the definition which we used last time was the most convenient way is to write this down in terms of determinants. So we have here the standard basis vectors I, J, and K, and what we write here is the components of the vector A, and what we write here are the components of the vector B. Okay, so this is the most convenient way to write down the cross product. This may be not identical with the definition you have seen in high school, because you told me last time that you haven't encountered determinants yet. So this kind of symbol, okay, there are actually 2 ways how to memorize, how to compute it. The first way to memorize it is, okay, you take this one, I times, and then you take away, because you look at this one, so you take away the first column and first row, and you look at the subdeterminant. So it's I times this subdeterminant. Then you look at this row here. You look at this row. So then you look at the second one, J. For the second one, you have negative J, and again you take those 2 you take this row and this column away, and you look at the subdeterminant times plus, and then you look at this one K, and now everything is again positive, and you take away this row and this column, and you get this subdeterminant. This is one way to compute this symbol. You will then, in linear algebra, you will learn why, because there is a rule behind it, Lagrange's rule, which tells you that in general determinants can be computed like this. This is the first way to, if you haven't seen determinants, just take it as a definition that this determinant, the value is defined by this. And another way to define the value of such a determinant is, you might have seen this as well. You take the first and second column and write it at the end, okay, and then you compute, and then this symbol is computed as follows. So you multiply those 3, plus you multiply those 3, plus you multiply those 3, and then minus you multiply those 3, minus you multiply those 3, minus you multiply those 3. Okay, this is another way to compute the value of this determinant. And if you do this, you will see indeed what you get here corresponds with the definition. Okay, so there are different ways to compute such 3 times 3 determinants. For us, this is just a convenient tool to write the cross product, nothing more. But in linear algebra, you will learn why, as for why we define such a symbol. So there's a reason behind it. Actually, this what you see is not the definition. This what you see is already a result. Okay, but for us, this is just a convenient notation to write down the cross product. Now, something which is true, which you will learn in linear algebra, which is true for every determinant, easily checked for using the definition of a 3 times 3 determinant, is if 2 rows or 2 columns are the same, then the determinant must be equal to 0. Okay, so if for instance here the vector b is identical to the vector a, then you will have that the second row and the third row is the same. And in such cases, you can, in general, for a determinant, you can always show that if 2 rows or 2 columns are the same, the determinant will be equal to 0. So you see from this property, if you know this for determinants, this simple property, you see that if b is equal to a, then the cross product will be equal to 0. Okay, so because once more, if you use this rule in order to compute the cross product of A with itself, then you have here A1, here A2, here A3, here A1, A2, A3. And because the second and third row are the same, so this determinant must be equal to 0. Okay, so this holds for all vectors. Now, you know that this is one way to define it. Maybe you have seen a different definition in high school or in classes like on physics. You know that the first thing which we normally prove is some properties. Namely, the first thing you observe is that this vector here is orthogonal to both A and B. So this is normally the first result. So it's like we have this result here. So A is orthogonal to the vector product of A and B B is also orthogonal to the vector product of A and B. That's the first property, and easily proved, because if you the only thing if you have to prove something like this here, you have to prove that 2 vectors are orthogonal. What you normally use is the dot product. So you just prove that the dot product between those 2 is equal to 0. But the dot product, by definition, okay. So you see that if you have 3 vectors and you compute the cross product of B and C and then the dot product with A, by definition, okay, you can easily check that by definition this is just a determinant of this matrix here, okay, because you see that because what you have to do is in order to compute this, you have to replace I by the first component of A, J by the second component, K by the third component. That's the definition of the dot product. So you immediately get that if you take first the vector product and then the dot product with A, what you get is this here. Okay, and so in this situation, okay, you see that if you compute the dot product of A with the cross product of A and B, what you have is here is the vector A, the components of the vector A, here the component of the vector A, here the components of the vector B, and you have two rows which are the same, so must be 0, which already proves this. And in this case, you see that the first and last row is the same, 0. Okay, so I do not have, once I understand determinants, you see I do not have to do any computations here. This might be a little bit different to how you have done it in high school. Of course, you can write down all the definitions, and you can do the computations, and you will see indeed the dot product of A with the cross product of A and B is equal to 0. But this is a more convenient way to see it. So this is normally the first result you prove, and then what you prove next is, so this is the first property, and then what you prove next is that if you compute the cross product, if you compute the length of the cross product between A and B, then what you get is the length of A times the length of B times the sine of the angle between A and B. And the angle we defined last time. So actually two vectors, you have two angles. Okay, like here we are in the space, but if you are in the plane, two vectors, two angles. One is this and one is this one. And normally we take so the angle between two vectors is the smaller of those two. Okay, so you see, this can be easily proved. You find the proof in our textbook, more or less just computation. And once you have those two properties, you understand already pretty well what the meaning of the cross product of A and B is, because you have two vectors in the three-dimensional space. Now you see from the first property, this the cross product, which is a new vector, is orthogonal to both A and B, and from the second you get the length. Okay, so this already determines more or less which vector the cross product of two vectors is, namely. Okay, so we have here A, we have here B. Okay, and we know now that from this property we know that the cross product, that's the new vector which we are interested in, is orthogonal to both A and B. Okay, so it must be orthogonal to the plane which is spanned by A and B. So A and B spans a plane, and the vector, the cross product of A and B must be orthogonal to this plane. And this here tells you something about the length of the cross product. So from this you know that okay, so from the first property you know that that the cross product, okay, is pointing, has the same direction as this line here, and from the second one you know the length. So there are only two choices left, namely either this one or in the other direction. Okay, so this result here determines, almost determines already the cross product. Okay, but actually the last property, you know from high school, you know from physics, which is sometimes the definition of the cross product. Maybe the definition you have seen in high school is that the cross product is defined as the vector which is orthogonal to both A and B. Okay, then has this length here and points in which direction. For this you use the so-called right-hand rule. So you take your hand like this, and then your thumb points in the direction of the cross product. Okay, so you get this here. So the cross product for this situation, okay, the cross product would be, if you interchange A and B, it would be in this direction because you have to do like this. Okay, but if you have A and B like this, then the cross product will point in this direction. So this here will be the cross product. The vector with this length here. But actually from the definition, you observe that from the definition to prove this, okay, because this and this is easy to prove from my definition. Okay, but to prove that out of those two possibilities which are left, okay, this is the one, okay. It's not so, I mean, it's not really complicated, but it's not so easy because first you have to say, okay, what do I mean, okay, by pointing up and pointing down, okay? For this, obviously, I have to take the coordinate system into account, okay? Because if you have a plane and you do not have a coordinate system, okay, how do you define up and down? Okay, there is no way differing up and down, okay? So what you need is a coordinate system, okay? And you have then to define up and down with respect to the coordinate system, okay? And you can think about how, that this last property, okay, to prove that the vector points in the direction given by the right-hand rule is not so easy to obtain from the definition of the cross product I gave, the direct definition where you just say, okay, this is the vector having these three coordinates. Okay, so you see that because I said this is normal. This is the definition maybe you have seen in high school or in physics. But since here we start by defining the cross product as a certain vector, okay, we have to prove that okay, this vector. We saw that those two properties. This is what you should realize. Those two properties, easy, okay, to prove. But to figure out which one, the one pointing up or the one pointing down, okay, wouldn't be so easy. It's not so easy. Okay, now because of this property here, this gives you already one useful result. Namely, you see that the vectors A and B will be parallel if and only if the cross product is equal to 0. Because if this is equal to 0, you see that you just have three choices. Namely, A is the 0 vector, B is the 0 vector, or here the theta is either 0 or pi. 0 means that the two vectors point in the same direction, parallel, and pi means they point in opposite direction but are also parallel. And by assumption, okay, the 0 vector is parallel to every vector. Okay, we also say that the 0 vector is orthogonal to every vector. Okay, so the 0 vector is both orthogonal and parallel to every vector. The assumption. This is sorry. Mm-hmm. This is a good question, actually. This is a very good question because it depends how you define the cross product. Okay, the way the cross product is defined in our textbook is okay. You say okay. So our definition of the cross product in the textbook is this one. Okay, you define the cross product as this vector. Then you have to prove it. Okay. Then you have to prove that it's this vector, because just from this definition you cannot see this. Okay. Those two properties are easy to prove, and you find the proof in our textbook. The last property, that the direction is given by the right-hand rule, is not proved in our textbook. The reason is because this is not so easy to prove, because you have to first you have to make clear. Okay, you have to define what is, like, if you have a plane, what is up and what is down. For this, you need the coordinate system. Okay, and our textbook does not provide these details. So, but the essential thing is, if you define the cross product like this here, then you have to prove it. Okay, because if you define the cross product like this, you have already the cross product. So you have to prove that it satisfies these properties. But you can take another route, and this other route is taken very frequently in physics or in high school. Namely, you do not use this definition. You define the cross product as the vector which is orthogonal to both A and B, which has the direction given by the right-hand rule and this length here. And then you have to, and then in high school normally you prove this. Okay. So this is a different way to introduce the vector product. The cross product. The vector product is the same name. Does this answer your question? Okay. So the main thing is, in our textbook, the author should prove it, but it's not proved in our textbook. The property that the direction is given by the right-hand rule. Only these two properties are proved. Okay. The reason why the author does not prove this, that the direction is given by the right-hand rule is because this is the not so easy part. It's the not so easy thing to prove. The other things are quite trivial. It's a very good question. Essentially, this is the essential question. It's something which is a little bit confusing in our textbook, because I'm not sure whether the author points out that this direction given by the right-hand rule, this is something you have to prove, because from those two properties, two possibilities are left, and you have to rule out one of them. Okay. So you see that from this you see already that the vector product is a convenient tool to figure out whether two vectors are parallel or not. Namely, you compute the vector product. If it's equal to 0, then the two vectors are parallel. This is if and only if. If and only if result. Now, for this, coming from this formula, you also get the easy, you also get the convenient or easy explanation of the lengths of the vector product. You know this from high school. If we look at A and B, then you see here we have the length of B. Okay, so the length of this vector. Here we have the length of A. And if we look at this here, so this will be theta. And if we look at this here, okay, then we know that, okay, this is the length here is the length of A times sine of theta. So you see that the area of the parallelogram spanned by A and B, so this parallelogram, okay, the area of the parallelogram is given by the length of the cross product. So you can use the cross product of A and B in order to compute the area of a parallelogram which is spanned by A and B, also of the triangle and so on. So you know this from high school. So the length of the vector product has this easy interpretation. Okay, so once more to summarize, the vector product is orthogonal to both A and B. The length is given by the area of the parallelogram, which is spanned by A and B, and the direction, whether up or down, is determined by the right-hand rule. Okay, so this is the vector product. The next question, which we normally discuss, is, okay, which kind of properties does the vector product satisfies? I mean, as an operation. So, for instance, normally if I have an operation like the normal addition, we want to have some properties like we want to know have that that A plus B is equal to B plus A, so that the sum is satisfying the so-called commutative law. Or another property we want to have is that A plus and then brackets B plus C is equal to brackets A plus B plus C, because then the order in which we do computation is not important anymore. It's so-called associative law. Now, unfortunately, the vector product is not so convenient. It's not such a convenient operation because many of those laws it does not satisfy. So, for instance, if you compute I times j. Okay, so of course, because you know already these properties, you know this will be a vector which is both orthogonal to eigen j. Then it must have, because of this property, must have length 1. So and it is determined by the right-hand rule. So it's k. It must be k, the third standard basis vector. But if you compute it in the other way around, okay, then the direction will change. Okay, because of the right-hand rule. Here you have I is like this here. I is like this, then j is in this direction, and the vector product has to point up. But here you have to apply the right-hand rule like in the other direction. Okay, so you see that j times I is not equal to k; it's equal to minus k. Okay, so which means that this is already not very convenient, because this means that this operation does not satisfy the rule that I times j is equal to j times I. Okay, it's not satisfied. Also, the associative law is not satisfied. So, for instance, if you look at I times and then I times j, okay, so you see that this is because this is equal here to k. Okay, and now you have okay, so here. This is I, this is j, this is k. Okay, so what do we have? We have I times k. So we have like this here. Okay, so what you get is minus j. But if you do the same computations with the brackets different, so first this one I times I, and then times j, then you see that because we already have seen that the cross product of a vector with itself is equal to 0. So what you have is 0 times j, okay, and 0 times any vector is equal to 0. So you see, and those two are not equal. So you see also the associative law is not satisfied by the vector product. this makes it somehow inconvenient because some of the rules, some of the laws which you know from, which are satisfied by addition, multiplication, and so on, are not satisfied by the vector product. But there are other laws which are satisfied. I just copy them. You find them in our textbook. So for instance, you can prove that, okay, so the first one is always true. So the commutative law is not satisfied, but it almost holds. Namely, if you interchange the order, then the only thing which changes is the direction. Now, if you multiply A with a scalar and then compute the cross product with B, this is the same as you first compute the cross product and then you multiply with a scalar, or you first multiply B with the scalar and then you compute the cross product. So here actually it doesn't matter how you do computations, whereas if you have 3 vectors and you have to compute the cross product of them, it matters in which direction. Then you have this rule is satisfied. This is called normally the distributive law. So you have if you have a sum here, the vector sum, and you multiply with you use and the cross product with a vector, then you can indeed compute this as okay, you multiply A with B and then you sum with the cross product of A and C. So this is convenient. At least this is satisfied. Also in the other direction it's correct. So if you have A plus B times C, then you can do the same. So you have A times C plus B times C. So then we have some exotic rules like this one. A times the vector product of B and C is equal to the vector product of A and P dot product with C. So this is kind of a more exotic rule. And then you have, but we will use this. We will need this rule later on. A times P times C is equal to the dot product of A and C, and this will be a scalar. So the scalar product with B minus, and then the dot product of A and B. Also, this will be a scalar, so the scalar product with C. So you have something like this here. Okay, so that you indeed have a couple of rules which are satisfied. All of them easy to prove because you just use the definition, plug everything in. You introduce components, plug coordinates, plug everything in, and do the computations on the coordinate level, and just show that the right-hand side and the left-hand side are equal. So the proofs are, of course, trivial. Exercise for high school students. Now, this one is an important one. Okay, so we saw already that if you compute the cross product of B and C and then a dot product with A, this in terms of determinants, this can be computed. This is just the value of this determinant here. Okay, and this product has your own name. It's called scalar triple product. Okay, so the scalar triple product of 3 vectors is defined like this here. And you see by this rule, it does not. You could equivalently define it like this here. Okay, there's no difference because you're getting the same. Now, why are we interested? So maybe this you haven't in high school. Why are we interested in the scalar triple product? This is easy to understand. This is B, and this one is C. Now those 3 vectors will make up a parallel epipede. And I have to copy this word from my, because I'm never sure a parallel, is there 1 L or 2 L's? I'm never sure about this. So what is a parallel epipede? So this is a generalization of the parallelogram to the three-dimensional space. So you have kind of a box, but the box is skewed. So you have something like this here. Then you have the same here. Okay, okay, it's not very pretty. So actually, you have the box here, which is spanned here by those three vectors A, B, and C. And now you see that okay. So if I project A, onto this line here, and if I denote this angle here by theta, then you see that the length here of this line is the length of A times the cosine of theta, but this here is the height of the parallel epipede. So if you want to compute the volume of this parallel epipede, what do? You compute the area of the parallelogram spanned by B and C multiplied with the height. So what you have is this area here of this parallelogram, but this area we know already is the length of the vector product of B and C, and then you multiply it with the height, which is given by the length of A times the cosine of theta. And you see what you get here is just a scalar triple product. Okay, so this is A times the cross product between B and C. Okay, so the scalar triple product is a scalar. Okay, and the meaning of the scalar triple product is it gives you the volume of the parallel epipede spanned by A, B, and C. And this has a simple consequence, namely the scalar triple product is zero if and only if the three vectors A, B, and C lie in the same plane. So, and this is called coplanar. So three vectors are coplanar if and only if the scalar triple product is equal to zero. So the scalar triple product is a convenient tool to determine whether three given vectors are coplanar or not, lie in the same plane. But the only thing you have to do is you compute the scalar triple product. If it is equal to zero, then you know the three vectors are coplanar. Okay, so this is maybe something new, the scalar triple product. We are not going to use it extensively, but just that you have heard that something like this exists. So any questions? Any other questions to the cross product? I guess this maybe it was a little bit different as you have heard things in high school, but more or less you have learned this already in high school. The main reason why you look at the cross product in high school, what is the main reason you look at the cross product in high school? Why do you introduce it in high school? Yeah, because it's a convenient tool for, if you're in the space, you have two vectors, it's a convenient tool to compute a vector which is orthogonal to both of those two vectors. This you need normally because you know that if you have a plane in the space, in the three-dimensional space, then in order to find an equation for the plane, what do you need? You need a vector which is normal to the plane, and you need a point inside the plane. This is enough in order to find the equation for the plane, or a vector which is normal to the plane, and the point in the plane will completely determine the plane. Now, this means if I give you 3 points in the three-dimensional space, okay, what you need to find normally is a vector which is parallel to the vector which, if the points are a, b, c, then you normally, if the first thing you compute is the vector ab, then you compute the vector ac, and then you need the vector which is orthogonal to both ab and ac, and for this you normally use the vector product, which is a convenient tool to compute such a vector. That's the main reason why you introduce it in high school. And this is also from this you already see that something like this doesn't make sense in the two-dimensional space. And also in the four-dimensional space, there cannot be something like the cross product. Or at least you have to think carefully what should a generalization to the four-dimensional space of the cross product be. Now, but in this class, we are not going to, later on we will discuss higher dimensional spaces, functions in higher dimensional spaces, but we will not discuss such functions extensively. I guess in linear algebra you normally discuss the properties of the n-dimensional space in more details. In case of a line, normally what you have is, okay, you have a vector v, vector which points in direction of the line. And you have given a point on the line, or you can the point on the line you can also describe by the tip or the end point of a vector which is considered to be positioned in the origin of our three-dimensional coordinate system. So you have a vector with tip on the line. Okay, and if you have this information, then it's easy to describe the line. Namely, our line is equal to the vector plus all the vectors which are multiples, scalar multiples of the vector v, and this is called the vector equation of the line. So what you describe here is the way you describe here the line is as a set of what you do is you have a set of vectors and you look at the tips of those vectors, and the tips will trace out the line. So this is what you called in high school vector equation of the line. Now, the next step is normally to introduce coordinates. So if you introduce coordinates, let's say r is given by x, y, and z. Let's say r0 is given by x0, y0, z0. Then you can write this in the equivalent form. X is equal to. I should also introduce v, which is a, b, and c. So then you have x is equal to x0 plus t times a. Sorry, this is not a vector. Then you have y is equal to y0 plus t times b, and z is equal to z0 plus t times c. And this gives you another way to how to describe a line in the three-dimensional space, and this is normally called parametric equations of the line. Okay, and those numbers here, there is a own terminology for those numbers. They are called the directional numbers. Or direction numbers, I'm not sure how the textbook calls it. Direction numbers. So those A, B, C are normally called the direction numbers. Okay, so this is terminology, this is terminology, this is terminology. Okay, and there is yet the final way to describe a line in the space, which you get by eliminating the parameter here. So what you have then is, so what you have to assume, let's assume that A, B, and C are all not equal to 0. So this special case, then you get that x minus x0 over A is equal to y minus y0 over B is equal to z minus z0 over C. And this way to describe a line is called the symmetric equations. Okay, so symmetric equations. The line. Okay, so you have these three possibilities how to describe a line in the three-dimensional space, either by giving a vector equation, or by giving a parametric equation, or by giving symmetric equations. And normally it depends. Okay, how it depends on the example. It depends what is given from the line. This will normally determine which of the three forms you're going to prefer. Okay, but you learned this in high school. I do not want to spend too much time discussing things like this. You also find some examples, easy examples, in our textbook. In particular, you have one example where you have two lines in the space, and you have to show that they are skew lines. I just want to remind you that what this kind of terminology means. So two lines are skew lines, means that they neither intersect nor parallel. So they're not parallel, and they do not intersect. These are called skew lines. Okay, so this is for a line. Now, how about a plane? Okay, so in order to determine a plane in the three-dimensional space, what you need, and you have discussed this in high school as well, is a vector which is normal to the plane and a point inside the plane. This will be enough to determine a plane. So what we have here is, okay, so we have a vector, call it n, or n0, normal vector. To the plane, and you have again a point in the plane, or we can represent the point as a vector, so that the tip of the vector will be the point which is inside the plane. So vector with tip inside the plane. Now, if you wanna describe the set of all vectors whose tip is inside the plane, then what you can do is, okay, if R is such a vector, you you subtract from this vector this vector R0. This will be a vector which is inside the plane, and this vector has to be orthogonal to the normal vector. So you have this equation here. Okay, so this equation will describe a plane, and this is called the normal equation of the plane. And again, you can introduce coordinates. So our n0 is equal to a, b, and c. Our r0 is equal to y0, z0. Our r is equal to x, y, and z. These are the coordinates of r. And then you can rewrite this as follows. So this means a times x minus x0 plus b times y minus y0 plus z times z minus z0 is equal to 0. So this is another way to describe a plane, and this is called the I forgot how parametric scalar equation. Actually, this is not the most important one. So the textbook calls this one scalar equation of the plane, terminology which is not frequently used. More important is the following equation in order to describe a plane. Namely, from this one you immediately get that you have this one ax plus by plus cz is equal to some d, and this is the normal form you know, and this is called a linear form. Linear equation of the plane. Okay, so in particular, you see that if you have given the linear equation of the plane, something you know from high school, then a, b, and c make up a vector which is orthogonal or perpendicular to the plane. So you see this already from this here. So we have here three different we have again 3 different ways in order to give a plane, either by a normal equation, or by the scalar equation, or by the linear equation. This is the most frequently. This is the one which we will use most frequently. And our textbook says that it can be proved that whenever this vector, the vector with coordinates a, b, c, is not a 0 vector, then then this equation indeed describes a plane. So this is what our textbook says. But of course, this is something completely trivial. And I think there is even an exercise in this chapter which asks you to prove that whenever the vector with components a, b, c is not equal to the 0 vector, that this describes here a plane. Rather trivial exercise. Okay, so this is the way, I guess, how you have denoted things in high school. Now, the next thing normally we define is 2 planes are parallel. So the 2 planes are parallel is easy to check if you look at the normal vector of the plane, because two planes are parallel means that the normal vectors must be parallel as well. So you just have to check. Well, if you want to check the 2 planes are parallel, the only thing you have to check is that the 2 normal vectors, which you can immediately read off, are parallel, which is equivalent to the cross product is equal to 0. This is an easy way to check it. Or there are also other possibilities. If 2 planes are not parallel, then of course they will meet. They will intersect in the line. Normally, the angle between those 2 planes is defined as the angle between 2 normal vectors of the plane. And we have seen that the symmetric equations which we use for the line, which was x minus x0 over a is equal to y minus y0 over b is equal to z minus z0 over c. The symmetric equations of a line just tell you that just define a line as intersection of 2 planes. Now it's very easy if I give you two planes, okay, you have done maybe thousands of such examples in high school. If I give you 2 planes, so I give you 2 such equations, okay, compute for, and the planes are not parallel, okay, compute an equation for the line of intersection. It's a very easy exercise which you have done in high school, I guess. And this is one of the examples where the vector product comes in very handy, because if I give you 2 equations, okay, from the equation you can immediately read off the normal vector, and then you compute the cross product of the normal vectors, and this will be a vector which is in direction of the line of intersection. Okay, so it's the most easiest way to compute the line of intersection. Then you have already a vector which is in direction of the line. What you need is a point, but a point you can easily find by equating by setting, for instance, z is equal to 0 in both equations and solving for x and y. Then you have a point, and then you can immediately set up the line. You'll find an exercise like this in our textbook, but I guess you have already seen such exercises in high school, and I guess many of them. Okay, what else? Let's maybe just do one example. Okay, so let's assume we have given a plane. Okay, so let's say the plane is given by ax plus by plus cz is equal to, or plus d is equal to 0 by this linear equation. Let's assume we have a point I should denote it by x0, y0, z0. So let's assume we have a point which is outside the plane. Now, what you have discussed in high school as well is, okay, what is the shortest distance between this point and the plane? Now the shortest distance is you easily see that the shortest distance between this point and the plane is reached so what you do is you choose a normal vector of this plane here, and then you set up the line with direction of the normal vector and going through this point here, and you see that so you have here angle of 90 degrees, and you see that the shortest distance is given by this distance here. Now, I just want to remind you that you have seen a formula in high school for this distance here. I just want to remind you the way to prove this, because there are different ways to do it. Like one way would be, okay, you really set up the line going through, having as vector in direction of the line, the vector ABC going through the point, you intersect it here and you compute this length. This would be the stupid way to compute it. Okay, the much more better way to compute this distance is using projections. So what you do is, okay, you pick any point in the plane. Okay, so this, let's say this is the point P with coordinates x, y, and z, and then you look at this vector here. Okay, so the vector from P to P0. So this vector has coordinates x0 minus x, y minus y 0, sorry, y0 minus y, z0 minus z. And the only thing which you have to do is you have to project this vector onto a vector which is in direction of this plane here, and you have to determine the length of this projection. And this is something which can be, because you see that a vector which is in direction of this line here is, you can read off from this here, so you have A, B, and C. Okay, and now if you wanna have this distance here. Okay, so the most easiest way to compute this is using the scalar product, the dot product. So if you, the only thing you have to do is you have to multiply those two and divide by the length of this one. Okay, so you have this vector dot product with this vector divided by the length of this vector. Okay, and you see that what you get here is, okay, so you have A times x0 minus x plus B times y0 minus y plus C times z0 minus z over, and the length of this vector is given by this formula here. Okay, and you see, because this point was chosen to be on our plane, so A times x plus B times y plus C times z will be equal to D. So you get okay, the absolute value of A x0 plus B y0 plus C z0 minus D divided by the length of A square plus B square plus C square. Okay, and this is the formula you have learned in high school. Okay, so you see that there are different ways in order to obtain these formulas. Okay, some ways are very stupid. I mean, very lengthy. Like if you, of course, you can do it different. Once more, one different way to do it would be you set up the line which has which is in direction of this vector, which is going through this point here. You intersect the line with the plane, you get this point here, and you compute the length between those 2 points. But this would be a very rather stupid way to do it. Here you really see the advantage of the dot product. Namely, I told you last time that dot product essentially has 2 important applications. The first application is it's a very convenient tool to check whether 2 vectors are orthogonal or not. And the second application which you frequently encounter is something like this here, doing projections. And here, once you realize you can use the dot product in order to compute this length here just by projecting this vector onto a vector in direction of this line here, things are very easy. Okay, so any questions to this? Now we will do some exercises in the assignments, not too many, because I know that you have done many exercises already in high school, and there's no way of lingering. There's no reason. There's no reason that we linger here longer. Okay, so this is indeed a cylinder, but a very specific cylinder, so-called circular cylinder. Now, in more general terms, how do we define a cylinder in mathematics? So a cylinder is made up by the set, or that's maybe even more formal, it's the set of all lines that are parallel to a given line and pass through a given space curve. Okay, so this is for us a cylinder. So looking at this notation, okay, what does it mean in terms of, for instance, this example here? Now, so for a cylinder, in order to describe a cylinder, what I have given normally is a line and a space curve. Okay, so in this case, the line which I have given is like this one, this line here. Okay, and the space curve which I have given is this one. Okay, and now the cylinder is made up, as you see here, it's a set of all lines which pass through the space curve, okay, and are parallel to this line. Okay, so this is the cylinder in this case. So you see that, normally you see from this what a cylinder can be described by an equation in the space which does not involve one of the variables x, y, or z. Okay, because for instance, if you have given in space like this one, z is equal to x squared. Okay, so this is an equation which does not involve y. Okay, then this will normally make up a cylinder because this will describe you a space curve, and then you have to because the y direction is arbitrary, so the y direction is this line here. Okay, so here in this case, if we draw this, we have here x, we have here y, we have here z. Okay, so our curve is so this yellow curve here is given by this one. And our cylinder is made up, and our line is the y-axis. Okay, and our cylinder is made up by all lines which are parallel to the y-axis and pass through the given space curve. So in this case, you get something like this here. Okay, you get something like something like this here. Okay, and so this is also a cylinder. Okay, this cylinder is called hyperbolic cylinder. No, sorry, parabolic. Sorry. The word which we use in order to describe the cylinder normally refers to the space curve. So in this example, the space curve, if you forget about the y direction, is a parabola. So the cylinder is called parabolic cylinder. In this case, the space curve is a circle. So this one is called circular cylinder, and so on. Okay, so this is the first type of surfaces which we are interested in, cylinders. So cylinders can be described by equations in x, y, and z, where one of the variables is missing. Okay. Now, what we are interested next are so-called quadratic surfaces. Now, if you compare, so maybe I first write what a quadratic surface is. Now, a quadratic surface is a surface which is described by an equation of the form ax squared plus b y squared plus c z squared plus dxy plus c xz plus e plus f yz plus g x plus h y plus I z plus j is equal to 0. Okay, that's why it's called a quadratic surface, okay, because it's described by a quadratic equation. Now, if we before we go on and look at the space, because here we are in the space, okay. Normally we are interested in classifying, okay, how many different quadratic surfaces are there which are not cylinders, okay. We exclude the case of a cylinder. You see, all the cylinders are contained as special quadratic surfaces, okay. But the cylinders are not really because they miss one of the variables, okay. So we want to exclude them. We want to understand how many different types of quadratic surfaces are left. If you look at the same problem in the plane, okay, in the plane, you give any quadratic equation of this type, but you forget about everything which contains z here, okay. The same problem in the plane. So you forget about this here, you forget about this here, you forget about this one and this one, okay. You ask the same question in the plane. You know the possible types. There are only three. You learned them in high school, namely hyperbola, parabola, and ellipse. Okay. So the corresponding curves, quadratic curves in the plane are those three: hyperbola, parabola, and ellipse. And what we want to do here is we want to introduce analog structures in the space, okay? And we will see that in the plane you have only three. In the space you have six possible types, okay? So the first thing normally you have to observe is you can forget about some of them because you can, by using translation and rotation, okay, you can bring them in a standard form, okay? So it can be proved that starting from this equation, okay, you essentially have just to consider two types of more simple equations. Now those two types are the following one. So this can be reduced to the following two types. So a x squared plus b y squared plus c z squared plus j is equal to 0, or and the second type is a x squared plus by squared plus cz is equal to 0. Okay. So what I mean is, normally if I want to classify all possibilities for such surfaces, okay, I do not care whether it's like if you look at for instance, if you look at the same problem in the plane, okay, so the ellipse is one type, okay, but I do not care whether I move it somewhere else, okay. If it is moved somewhere else, it's the same type for me, okay. So and also rotation gives just the same type for me, okay. So if I place this ellipse somehow here, then okay, it's still the same type, okay, but a different equation, of course. So the first thing, if I have something like this here, and I want to understand, okay, which different types do I have, is okay, I try to reduce this equation such that all the types which I get by like rotation or what's called translation, shifting to somewhere else, okay, I just consider the same for me. So using this, I can reduce this general equation, okay, to the discussion of just those two here. Okay, I think there are some examples in our textbook which shows you how to reduce this by just using translations and rotations to this case and to this case. Okay, but this is something you have to believe me, because these are just details. So what we have to do is, okay, we have to discuss those two types here. Okay. Now, how many are left? Okay. So essentially, if you have here, for instance, if A, B, C is larger than 0 and J is smaller than 0, okay, then I do not care about the specific numbers A, B, C, and J. Okay, I will call this one type. Okay, so you see that, for instance, by looking at this equation, I just have to look at what are the possible combinations for the sign. Okay, so for instance, all of them positive, or only one of them negative, all other positives, and so on. If I do this, then you see that if I have, if I look at things like this, okay, I do not have to discuss the case where 3 are negative, 1 is positive, because then I multiply everything with -1, and I get 3 are positive, 1 is negative. Okay, so I only have to discuss the cases where I have where either all of them are positive, or one of them is negative, or two, at most 2 of them are negative. These are the cases which I have to discuss here. Okay, all of them are positive. A, B, C, and J are positive. Okay, it doesn't give an interesting structure. Okay, so I can forget about this case. So what is left is I just have to consider either 1 is negative or 2 are negative. Okay, and this will give me the types. Okay, now the case for either one is negative. Okay, here either this can be negative or one of those can be negative. 2 types. Okay, for either one of them is negative. Okay, now the first type is. So I want to systematically understand which kind of types do I have. So the first type I discuss is this one is negative, all others are positive. Okay, so for instance, the case x squared plus y squared over 4 plus z squared over 9 is equal to 1. Okay, so the case where this here is negative, all others are positive. This is one type. Okay, so this one. Now normally, because we are in the space, okay, in the space things are hard to visualize, and we will in the sequel we will our main aim is to discuss properties of surfaces in the space. And next time I will show you that Maple is a very good tool in order to visualize space curves. If you do not have access to a computer software, to a program like Maple, okay, it will be hard to understand how such surfaces look like. So this will be also the main problem by passing from. Later on, we also want to do for surfaces. We want to, or for functions of 2 variables, which essentially, where the graph is a surface, we want to introduce things like derivatives. We want to do integration and so on and so forth. And the main complication. So essentially, what we want to do is we want to extend things we have done last semester for functions of 1 variable to functions of 2 and more variables. Now, for functions of 2 variables, it's already some of the concepts are harder to understand. The main reason is because it's for functions of 1 variable, we have a picture of a graph, and we can try to figure out in terms of the graph what is the meaning of for instance, our definition of the derivative. And this will be more complicated if we pass on to the 3-dimensional space. So this is normally a main obstacle when you learn for the first time these kind of things. But since now it's very easy because we have many computer programs, and maybe 30 years ago, 40 years ago, it was much more complicated because you couldn't visualize a lot of those surfaces. But now it's very easy because we all have access to a computer program like Maple, and I will next time I will show you that Maple is very powerful is a very powerful tool if you want to understand how surfaces like this here look like. This, of course, is an easy one. Okay. Now, if you do not have access to a program like Maple, the only thing you can visualize or you can try to understand how such a surface look like is by looking at cross sections. We have done this already last semester. So normally, what you do is, okay, you try to understand, okay. If you fix, for instance, Z, okay, which means you slice the surface by a plane which is parallel to the xy plane, okay, how does the cross section look like? You try to understand the cross sections in the 3 directions which are given by the coordinate planes, so parallel to the xy plane, parallel to the xz plane, parallel to the yz plane, and then from the cross sections you try to understand how the surface looks like. Sometimes this is successful, sometimes not, because sometimes the equation is much too complicated. Here, of course, it's simple. You see that if you fix z is equal to k, okay, then you get so this means we slice with the plane which is parallel to the xy plane. Then we get x squared plus y squared over 4 is equal to 1 minus k squared over 9. So we see that this only makes sense if k is between -3 and 3. Only in this range we have here solutions for x and y, and we see that for this in this range, okay, what we get as the cross sections are the ellipse. So cross sections are ellipses. Okay, and the same for the other directions. So you see, because everything is because here the sign is always positive. So if you do the same in y, you will see you also get as the cross sections ellipses. If you do the same in x, the same. Okay, so no matter how you slice this kind of surface, okay, either in xy, either parallel to the xy plane, or parallel to the yz plane, or parallel to the this is the yz plane, or parallel to the xz plane, you always get ellipses. Okay. That's the reason why the first type of the quadratic surfaces is called ellipsoid. So this one is called ellipsoid. And this essentially looks like you can visualize it like an egg, okay? Because if you have an egg and you place it into the in the origin of the 3-dimensional coordinate system, okay, more or less, no matter how you slice it, you always get more or less ellipses. Okay, so this is the first type, ellipsoid, and we will on Monday we will see there are 5 more types. Okay, so for quadratic surfaces, there are essentially 6 types. We will see one is the ellipsoid. We will see there are two types of hyperboloids. There are 2 types of paraboloids. And there is one cone, and these are essentially the 6 types of quadratic surfaces which correspond then to the 3 types of, you can say, quadratic curves you have discussed in high school. Okay, so next time we will complete this, and I will show you some animations using Maple.